Hey, I'm David. I'm the coordinator of the Maths Learning Centre, and you have a lovely fractal picture of me. It's semester 1, 2018. This is a Differential Equations revision seminar. That's enough of that. Okay. I have never given a revision seminar for Differential Equations II. I have given them for Engineering Maths IIA, which has some of the same stuff in it, which explains why certain other people are here, so well done. Yeah, so lucky you guys. Right, so the questions I have been asked online so far basically concern the Frobenius method and power series stuff, and then some other things. And then there's a smattering of other stuff. So I might do the power series stuff first, because that's the thing that so many people have asked me about. You will need to warn me if I say something that is wildly different from what your lecturer says, but it shouldn't be that different. And it would be helpful if someone had some lecture notes printed out that I could use. That'd be cool. Otherwise, I will use the ones that people sent me on the computer, which is not as easy to do, but I can certainly do. But otherwise, oh, how exciting! Let's see. Okay. Well, here we go. So, my understanding of the way this course works is that you differential equations, and you've been shown various ways that people of history have attempted to solve differential equations in various different kinds of equations in various different ways, and you try and understand the ways that these people did it. And they're not necessarily ways that you would come up with yourself, and you think, my goodness, how did they come up with this? But that's basically my understanding of it. And you've been given, please remember that you've given these to me. And feel free to send me an email if I forget to give them back to you or you forget to get them. Okay. Some waves. Vessel. Aha, this looks reasonable. Okay. Okay. So you started off with things that you could just rearrange and integrate. And then in Maths 1B there was, you carry on from that with some things that had constant coefficients, and then there were some fabulous PDEs, I think, that you separated into, say, well, what if the answer was like this? Let's hope that works. And basically that's pretty much the deal with the end of this course. It's all very much, here's a differential equation, what if there were an answer like this? And hope that it works. And it does. And magic, okay? So what we're going to do is we're going to solve differential equations by thinking, what if there was an answer like... That's not how you spell like. What if there was an answer like y equals 2x? So y is a0 plus a1x plus a2x squared plus a3x cubed plus forever. That's what we're going to do with a couple of modifications. So what if there was an answer like that? And we go, what if? And then we try and figure out what those a's are. And the reason why we expect there to be an answer like that is that most of the functions that we know and love have representations like this. That's what a Taylor series is for. This would be a Maclaurin series. Pardon me. So it's not the worst thing to expect that they should look like that. And also, I mean, in a lot of real-world situations, one of the best ways of approximating anything is to do a Taylor series for it. So it'd be kind of cool if you did it as a Taylor series, because then, you know, you might find that the answer is actually, you know, e to the minus x squared from some other method, and go, oh, I don't know how to calculate that, I'm going to need a Taylor series anyway. So you might as well start with a Taylor series in the hope that it gives you the thing that you wanted, you know, overall anyway. So I think the best way is probably to just pick an example and run with it and see what happens. And someone has helpfully asked for, in fact, someone sent one at 10 to 12, and there's a practice question in a practice exam. And, oh no, I might have to do one that isn't like that first. Okay, I might not do that one first. Let me just see. I'm just going to do a simple example off the top of my head just to make sure that I know what's going on first. So let's do an example. I will put things here in a minute. All right, that'll do. Is this a problem, David? Sure it is. Can you just not put that there? And despite the fact that I warned you about this seminar existing a week ago, you know, I've had 4 revision seminars since then, and a weekend, which I chose to have. And so I haven't prepared very much. So let's do this one and attempt to solve it. And I may put some initial conditions in later, so just leave a gap. Okay, so here's one, and we're going to assume that it has a solution of this form. Okay, so that's my series, and I might as well actually write it as an infinite sum. Like that. Okay, so what I'm going to do is I'm going to sub that in and see what happens. Like that. So the AN is just a number for each AN. All the ANs are just numbers, and they're multiplied on, so they'll still be there. And then I'll have to multiply by the current power and put the power down by 1, and I get this. It's really important here that I make sure I realize that when n is 0, this is going to be 0. Because when n is 0, it's just A0, and that'll go away. And so in a very important sense, this actually only starts at 1. I don't know if this is actually important, but it's a thing that I've seen people do, so I'm going to run with it and make sure it's important. I think the reason I do this is that I don't want to not that I'll ever do this, but I don't want to integrate this and think that I get an extra term that wasn't actually really there. So I'll differentiate it again, and so this an times n is a constant multiplied on, so it'll still be there. I'll multiply by the current power and put the power down by 1. And now the first 2 terms have vanished because I've done the second derivative, so it actually starts at n equals 2. All right, cool. Cool. I need to say, at any point, feel free to stop me and ask questions or make comments. If I feel like I don't want to answer or you're being rude, I'll let you know. But otherwise, I should, most of the time, respond perfectly happily. Yes?
Even with the lecture notes, they've written when they do the derivatives, it just always starts at 0.
Okay.
And then when they combine them, they have to start at 0 because otherwise you're talking about different things.
I will get back to that. So I think for this one I'm going to make it start earlier if that's okay, but for other situations we won't do this. So we'll try and draw commonalities between them. So if I don't answer that, ask again later, okay? Okay, so my actual, let's see if I can fit it all on the screen at once. My actual equation was this, and so I have my y double dash, that's good, but I need a 2x minus 1 times y dashed. And so I'm going to need to multiply this by 2x minus 1. And I'm actually, because of this is my own way of dealing with this, I'm going to multiply it by the 2x and the minus 1 separately. So I'm going to run my way through this equation and write them all down one at a time. So my y double dashed is n equals 2 to infinity a n minus 1 x to the n minus 2. Did that one. The next one is a 2x minus 1, so 2x lots of y dashed. So y dashed is this one, and I'm going to multiply it by 2x. And so I'm going to get 2an times n, and when I multiply this by x, it goes up to x to the n, because it was n minus 1 before. But then I also need a minus 1 times y dashed, which is that. And then I also need an x times y. Okay, so what happened, just to compare them, this one stayed as it was. This one got multiplied by both 2x, which is here, which made the power go up by 1, and by minus 1, which left the power as it was. And this one got multiplied by an x, which made the power go up by 1. And apparently, if I add all of these together, it comes out to 0, according to this. Like that. So, cool. I need to add them together. Now, the problem at the moment is that it's difficult to tell how to add them together because the ends and things don't line up. So this one starts when n is 1, so it goes x and x squared and x cubed and whatever. And this one starts when n is 2, so it starts with a constant and then an x and then an x squared. But it's hard to tell which one is the x squared and which one is the x. And when I add these together, I'm going to be wanting to add all the constants, and then I'm going to want to add all of the coefficients of x, and then all the coefficients of x squared, and so on. So it would be really useful if I made my ends line up. So I should shift them all over to be at the same spot. It doesn't really matter which one I shift them to, as long as I shift them all so that they're all x to the n, or x to the n minus 1, or x to the n plus 1. It seems convenient to make them all x to the power of n, because that's simplest. So I'm going to shift them all over. My method of doing this requires a lot of space, but I get it right. So, so this one, I'd like that to be an n. And so I will shift this one over to make this an n, which requires me to add 2 here, which means I'm going to want to be adding 2 to all these ends and subtracting 2 here. So n minus 1 plus 2 is n plus 1, like that. That one shifted over by 2. So all the n's in this part went up by 2, and these ones went down by 2. Of course, infinity minus 2 is still infinity. This one's already an n, that's fine. All right, this one has to be moved over by 1. So it'll be a n plus 1, n plus 1, x to the n. And I move this down by 1. Okay, that's good. And then this one needs to be moved back 1. So I move this down by 1 and this down by 1, so that all the ones inside go down and this one went up. And now all my x to the n's line up. Yep.
Where did the negative sign go? On the down, here.
It went into the ether. Wouldn't you love to have an observer in your exam to pick up your minus sign errors for you? In one of the Barbie movies, they have a fairy attendant at their school, and I would love a minus sign fairy. So we can now add these all together, but one of the problems with them is that they don't all start at the same spot. So they all have the same x to the power of n, and so I can pick a particular n like 4 and figure out what the coefficient of x to the 4 is by putting a 4 in for n. But the problem is that some of them start at 0 and some of them start at 1, and so the first couple are going to be a bit different. And so I'll be able to do something like when n equals 0, I've got the coefficient of x to the 0, so i.e. the constant. And so I've got, this one's got a 0, so I get a 2 times 1 there. This one doesn't have an n equals 0. This one's got an n equals 0. Like that. That's the constant term. And that is 0. Okay. Because the whole thing's supposed to be equal to 0. Okay, so I get 2a2 minus a1 equals 0. So it's traditional to rearrange that to get the later ones figured out in terms of the earlier ones. Okay. Sweet. And then when n is greater than or equal to 1, because all of my terms have a 1 in them. Oh gosh, let's see if I can fit this all in the same. No, just a second. I can put it over here because this is wide. So when n is greater than or equal to 1, I've got n plus 2, n plus 2, n plus 1. So that's the coefficient of x to the n, plus 2an times n minus an plus 1 times n plus 1 plus an minus 1 is 0. Because all the coefficients are supposed to be 0. Oh. All right. So the latest term here is an plus 2. And that's minus 2n lots of an plus n plus 1 lots of an plus 1 minus an minus 1. And that's it. And that's not at all helpful, really. It does tell me how to figure out each coefficient from the ones before it. Are we all good? I don't mind if we're not. Important thing to understand, which I should reveal at the beginning, is that I never did differential equations as a student. I have only learned differential equations by helping people in the Maths Learning Centre. So, yeah. Okay. There we go. So what does this tell us? So from this, it looks like I can figure out what an plus 2 is from the previous 3 terms. It's a bit distressing that it starts at n minus 1, but that's okay. If I wanted, I could rewrite this to say a n equals and do it in terms of the previous ones, and maybe that's a good idea. Maybe it's a good idea to say, so this was for n greater than or equal to 1, right? So let's shift everything over a bit. And subtract 2 from all these n's. Okay, so I just subtracted 2 from all the n's, because it should be true for every n. Yep. So this was true when this number here was greater than or equal to 3. So this was true for n greater than or equal to 1, and this is true at n greater than or equal to 3. So just make sure that works. When n is 1, this is 3, so that's 3. When n is 1, that'll be a 1, and 3 minus 1 is 1. 3. Yeah, okay. It's working for the first few. So that tells me how to figure out what an is from the ones before it. Sweet. Okay. Well, that I don't know if that helps. That's pretty much it. This starts at 3. And the other ones I'm just going to have to leave as they are. A2 is already a multiple of A1, so that's actually quite interesting. So let's see. Just to see, A0 is A0. This doesn't tell us anything about A0. So to sum up, A1 is A1. It doesn't tell us anything about A1. A2 is a half of A1. A3 would be minus 2 times 1 times A1 plus 2 times A2 minus A0 over 3 times 2. Okay, cool. But A2 is half of A1. So got 2A1. And A2 is half of A1. And so this 2A2, I'm just going to sub it in properly. I don't really want to do it in my head. I don't know if any of this is necessary. I'm just trying to understand what's happening here. So 2 minus a half of 2, so that's minus. All right. Cool. So it looks like each one of them is going to be able to be written as a combination of A0 and A1, which is good. It's a second order differential equation. It ought to have two unknowns when we find its solution as a general term. And so my two unknowns are A0 and A1. So if I were given initial conditions, I could, therefore, figure out what the A0 and the A1 actually were and start to figure out what the actual coefficients are. All right. I feel like doing A4, but I don't know if it's worth all the pain. Yeah, I'm just going to leave it at this. So what if, so now let's do a what if. What if also I had y of 0 was 3 and y dashed of 0 was, I don't know, 2. Well, then that would be telling me what the A0 and the A1 were. So I know that y of 0 is A0 plus A1 times 0 plus A2 times 0 squared plus and so on. which is just A0, which was 3. And so A0 equals 3. And y dashed of x, actually we have a formula. Y dashed of x would be A1 plus 2A2x plus 3A3x squared plus and so on. That's the derivative of y. And so y dashed of 0 would be A1 plus 2A2 times 0 plus and so on, which is just A1, and that would be 2. And so it tells me what A2, what A0 and A1 is, and that allows me to figure out the coefficients of my thing. So let's see if we can figure that out. Okay. So let's see, we have A0 is 3, A1 is 2, A2 was a half of A1, which is unhelpfully 3 on 2. A3 was minus a half of A1 minus a sixth of A0. Oh yes, that's much nicer. 1. Wow, 3, 2, 1. That's cool. You know, for a mild value of cool. So that's minus a half of 2 minus a sixth of 3. Because A1 was 2, yeah. So minus 1 minus half. All right, cool. Just for completeness' sake, I want to try and do this again. So A4, according to my formula, should be minus 2 times 2 A2 plus 3 A3 minus A1 over 4 times 3, just subbing into this formula here when n is 4, which is minus 4A2 plus 3A3 minus A1 over 12. And I know what all of those numbers are. A2 was 1, and A3 was minus 3 over 2, and A1 was 2. And so I can figure out what it is without actually having to do algebra to turn it into something involving A0 and something involving A1. I could just sub in the earlier values I already had. A2 was 1, and A1 was 2, and A0 was 3. Oh, sorry. And A1 and A3 was minus 3 over 2. Wow, it's not pretty. Well, minus 4.5 would be minus 8.5. Minus another 2 would be minus 10.5, which would be minus 21 over 2. So we have minus 21 over 2 on 12. And 21 divided by 3 would be a 7. So that's minus 7 over 8, I think. Because the 12 has got a 3 and a 4 in it, and I divide by the 3, and the 21 becomes a 7, and then, yeah, okay. Let's pretend that's the right answer, even if it isn't. And so we have now that my y is actually 3 plus 2x plus x squared minus 3 on 2x cubed minus 7 on 8x to the 4 plus other stuff. And that's probably accurate enough to do anything we wanted with our differential equation, actually. So I probably don't even need to know the rest if I want to do this to any level of precision. Which is the basic idea of this Taylor power series thing. It's like, I don't really care what the function is. This is precise enough for whatever methods I have, as long as my x is close enough to stuff. Because I imagine that my fractions are just going to get smaller afterwards. It's okay to leave it like that. And in fact, in lots of exam questions, it'll just say, write the first 5 terms. It won't tell you to do it. So exam questions will often ask you to say, what is this? What's the recurrence relation? Is that what they call it in DEs too? And also, what are the first some number of terms? Now, I'm just going to try and put my pages in the correct order. Right. So that's not the Frobenius method, that's just doing a power series. And the reason why that worked is because I didn't have anything multiplied by my y double dash. Because sometimes that causes problems. So let's just see what would have happened if there had been an x squared in this position here. If there'd been an x squared in this position here, then when I got down to this level, I would have had to times that by x squared, and then we would have got an x to the n. And then I wouldn't have shifted that one over, and my recurrence relation, I reckon, would probably have turned to crap. And I wouldn't necessarily have been able to figure out what was going on. So it turns out that sometimes, if the stuff multiplied by these things is, if there's something here that isn't straight up ordinary polynomial, that is 0 when x is 0, then weird crap happens. And sometimes it'll work and sometimes it won't, and so we're just going to have to find a different method of dealing with that. And that's Frobenius's method. So Frobenius's method is that in special circumstances, when there is something in front of the y double dash, you can just start your power series a little higher up. So it may be that, sure, it might be this, but actually it might be a0 x to the r, a1 x to the r plus 1, and so on. Now that's not necessarily going to be a whole number. You might actually start at x to the half. So what we're actually thinking is that we're multiplying this by x to the power of something, and it might just help to figure out what the answer actually is. And that's Frobenius's method. And so what I'm going to do is now do this exam question that someone asked me about. I will copy it down onto my page. Consider the second order ordinary differential equation blah for x greater than 0. Since x equals 0 is a regular singular point of equation 2, the equation has at least one solution of this form. Okay, I'm just going to run with it from here. I'm just going to write down the equation. It said some words there that might be worth talking about as well. Damn it. Do you know what? It's so early at the page, I'm going to start a new page. Okay, so xy double dashed minus 2 of x minus 1 times y dashed plus x minus 2 times y is 0. Okay. So the issue that we have here is that the thing that's multiplied by y double dashed is 0 when x is 0. And so, not that we really care because it's strictly greater than 0, but let's worry about that. And so that means that when x is 0, we don't actually have the same differential equation as we had before. And so what we're actually going to do is we are going to do Frobenius's method. And they talk about this thing called a regular singular point. Right. And that doesn't mean it means it's a singular point in a regular sort of way. So it's a singular point because if I write this in standard form with the y double dash without anything next to it, at least one of these functions is not analytic at x is equal to 0. Which means, well, often it means they don't exist, when x is 0. I mean, this function doesn't even exist when x is 0. But sometimes it means that it might exist, but it doesn't have a Taylor series, a Maclaurin series at that point. So, cool. So they are singular points. Okay, so since at least one of these damn it, it's not for, it's at. Not analytic at x is equal to 0, which in our case means it doesn't exist when x is 0. But sometimes means there's no Taylor series for it at that point. But pretty much in this course it always doesn't exist. I'm pretty sure. Okay? So it's not analytic at x equals 0, which means it's a singular point. And because of that, a traditional power series isn't going to work. Because if something's not analytic, it doesn't have a power series. And so I can't use a traditional power series for this because it's, it doesn't have one. And so I'm a bit stuffed. But if it's a regular singular point, then I can just use Frobenius's method. So to know if it's a regular singular point, if you multiply one of them by x and the other one by x squared, and I can't remember which one is which. Does anyone know off the top of their head? Second one's x squared? Okay, cool. That makes sort of sense. We sort of multiply this one by nothing and this one by x and this one by x squared. That sort of works. So if you multiply one of them by x and one of them by x squared, so the derivative one by x and the not derivative one by x squared, and it comes out to be analytic, then you're good. So let's have a look at this. Times x is 2x minus 1, which is analytic. And x minus 2 over x times x squared is x minus 2 times x, which is analytic. And therefore it's a regular singular point. So the fact that it was a singular point means that ordinary power series isn't going to work. Well, not a power series with just x. You know, a naught x plus a1x plus a2x squared. I could use a power series with like x minus 1 and x minus 1 squared and x minus 1 cubed. I could use a power series at a different place, but not at x equals 0. And so this says that since it's regular, the Frobenius method would work. And if it was a non-regular singular point, I don't think that's covered in this course. And therefore, I don't know how to do it. Okay. So Frobenius's method says that if you have a regular singular point, in particular when the regular singular point is x equals 0, then you can do a power series. It's just that everything's going to have an x times by x to the power of r. For some r in R. And I'm saying that because the r won't necessarily work out to be a whole number. So the r might be like a half or root 7 or 2 or 0 because the power series might actually work after all. But what it won't do is allow, so we don't necessarily know if r is a whole number or not. Okay. But we are going to do exactly what we did before and sub it into our equation, and so therefore I'm going to pop this over here. So I'm just going to copy my equation. Okay. So I still need to figure out what y and y double dashed are. So let's see, y was y dashed was m plus r. So the power came down and the power went down. So I'm not going to do the thing I did before, where I changed this to be 1, because I don't know if the r was like a half, then there'd still be like an x to the power of minus a half here, and that'd be fine. Okay, so that term can totally be here. It's not like it vanishes completely because it might be x to the, something else. So I'm going to leave it in there. That's why. So in the other one, the reason why the other one was helpful for me to move it is because moving them over helped me to see that one of the n's was different to the others, because the n equals 0 had a different number of pieces in its algebra than the n equals 1. Because the n equals 0 had 2 bits and the n equals 1 had 4 bits. Whereas this one, well, I just have to be sad that I can't do that. It probably would work fine in the other one, but you've just got to be really careful to notice when some of them are 0. So it's probably okay to not do that m equals 1 thing ever, but just when you sub it in, they come out to 0 after all.
But in the last one, so there's ones that come out because you can't sub it into 0. You just reduce them because you said the n has to be like an numeric
Yep, so when I look at this, where did it come from? Damn it, David. Over here. So I looked at this and went, oh, well, some of them have 0 and some of them have 1. If these had all started at, well, actually, these would all end up starting at different places, but if these had all started at 0, then when I subbed it in, I would end up with some of them being 0, like 2a 0 times 0. And that would be fine, but I would actually need to look closely when they came out to 0 and include those separately, because it gives you different sort of information. The recurrence relation is a little bit different when some of the coefficients are 0. So if you don't shift the beginning as you go when you do the derivatives like this, I reckon you're going to have to, when you get to this stage, look closely and see for the early numbers here, which of the terms come out to 0. And if none of them come out to 0, then recurrence relation starts straight up. But if some of them come out to 0, you're going to have to do the simpler ones.
The ones that didn't come out to 0, the ones that went there, you just cancel them out anyway.
Yeah. So I got rid of them when I did the derivatives. So when I got the derivatives, I said, oh, this one starts at 1 because when n is 0, it's 0 anyway. So I got rid of that right at the beginning when I did the derivatives. But I could do it later, but I would have to sub in n equals 0 and see if some of them aren't really there. And then sub equals n equals 1 and see if any of them aren't there. All right, cool. Sorry for that little interlude. Well, more like, no, not allowed to say sorry. Thank you for bearing with me in that little interlude. So my second derivative, I will take the derivative I already had, and so this is a constant multiplier, this is a constant multiplier. I'll multiply by the current power, and I'll get that. Okay, so there's some terms. Okay, and then if I want to substitute this into these equations, I should multiply by the appropriate things. Okay. If you don't mind, I'm going to rewrite my equation one more time. I just wanted to expand that bit out here. Minus 2 times x is minus 2x, and minus 2 times minus 1 is plus 2. Because of my method of subbing this in, it makes it easier for me to do them as separate things. So let's have a look. X times y double dashed. And then the power of x will go up by 1. It was minus 2, and now it's minus 1. Now let's see, minus 2x times y dashed So minus 2am m plus r x to the m plus r, but it goes up by 1 because I multiplied by x. And plus 2 times y dashed is this. Sweet. And then x times y is this. X times y. What's y? This. So am x to the m plus r plus 1. And finally, minus 2 times y is that. Okay. Sweet. So it looks like I've got 3 different places that this is. I've got several at m plus r, a couple at m plus r minus 1, and one of them is at m plus r plus 1. Which is sad. It would be much easier if there are only 2 of them, but there are 3. Right. I should probably say that the total is 0, just to remind myself what's actually going on here. And when I add all this together, which is here, it should come out to 0. Okay. So I'm not doing the question as it's stated in the exam. I'm just doing the long version so that I can see what could have happened. Okay. So, right. So if I wanted to add these all together as one sum, I would need to shift them over so that all of the powers of x are the same. And so I'm going to have to shift at least 2 of them because I've got 3 possible ones that I could be shifting. So what if I shift these 2 up to x plus r and this one down to x plus r? That sounds like it's going to be the simplest thing I could do. You get to choose, and it doesn't really matter. So you can choose to shift them all up to the biggest one, or shift them all down to the smallest one, or shift the one up and one down. It doesn't really matter. It'll all work out in the end. I don't know what your lecturer prefers, but he's clever enough to figure out what you mean if you do this. Am I brave enough? I really should have, I always forget to do this. I really should have left a bit of space between each of them in case I wanted to shift them over. That would have made my life a little easier. I'm sorry about that. So I want to shift them all over. So I want this one to go up 1, up to m plus r. So all of these go up 1, m plus 1. M plus 1 plus r, m minus r, because the minus 1. And so this will go down 1. This one doesn't change, so I probably don't need to copy that one again, but whatever. This one needs to go up 1 as well. And therefore this one will go down 1. And the x, y has to go down 1 because it was before it was an r plus 1. So a m minus 1. And that's going to start at 1. And this one stays the same. Sweet. This is where we are. It's all shifted over now. All right. So I can do exactly what I did before, and I just find the earliest m, and I find all of the m's where some of them don't have that number, or even not. I just find the earliest m, and then that earliest m is where the initial equation comes from. This is my understanding of how this works. So the earliest m is m equals minus 1. That's the earliest m that occurs in any of those. The first one starts at minus 1, the second one starts at 0, the third one starts at minus 1, fourth one starts at 1, and the last one starts at 0. So the earliest starting m is negative 1, and so that's where I'm going to start. And so I have a0 r minus 1 minus r. So that's my coefficient of x to the minus 1 plus r. And the next, the one where there's a minus 1 is this one. So I'll have 2a0 r, that's that coefficient, because it's a minus 1 plus, yep. And that's supposed to be 0. So they both have an a0r, so I'll take that out. And I'm left behind with a minus 1 minus r and a plus 2. And this whole process only will work properly if a0 isn't 0, and so we're just going to get our initial equation. That's my initial equation. There may be a quicker way of doing this, but I have to figure out what the power series is anyway. Okay. The a0. Sorry? Of x to the power of minus 1 plus r. I was subbing in m equals minus 1. I don't know what r is yet, so I can't do that. Okay. So now we have either that r is equal to 0 or r is equal to 1. So let's see where we've been. We said, well, suppose it was this power series but with a plus r on all of them as well. And if it really is this, then the only way that's possibly going to work is if r is 0 or r is 1. And r is 0 is nice because then that's an ordinary power series. Yay! But if r had come out to a half, then, all bets are off. Okay. All right. So now we're here. So normally what you do is you pick one of these r's and then you run forward from that point with everything in terms of that r. Now see, so there's three possibilities. They could be, that's where I'd have to look it up in the notes. They could be different by an integer, in which case there's something weird that happens. They could be not different by an integer, so like r is a half and r equals 1. That'd be, and you can just try them, do them both, and you'll get these two different solutions. And there's something else that happens too. So there's these three possibilities, and we'll have to just look them up. But for today, the exam question that I'm working from just says to do what happens with r equals 0. So let's just try them both. So let's look at r equals 0. Okay. Right, that's really not going to change all that much here, and I don't feel like rewriting this, so I'll just sub in the r equals 0 in a minute. So, even without looking at the r equals 0, I've already done my m equals minus 1. That was the earliest m. The next m that appears after minus 1 is 0, and so I'll see what happens when m equals 0. So when m equals 0, we have, this one has an m equals 0 because it starts at minus 1. So we have a1, 0 plus 1 plus r, and 0 minus r. Oh, that's not supposed to be a minus r. What the frill am I doing? Oh, it's a plus r. Minus fairy, yes, thank you. My own brain did it, but like, 20 minutes later. God, for the sake of frill. Right. Okay. Everything's okay. It's all good because we still have an r equals 0. Right. So x to the r, oh, we don't need the x to the r. So that's our coefficient of x to the r. So that's this one that had a 0. I'm going to put the r in a second. And when m equals 0, we've got minus 2a0 r. And when m equals 1, this one has a 0 in it as well, so that's 2a1 r plus 1. This one doesn't have m equals 0, and this one does. All right, so I've found all the ones that have an m equals 0 in them and collected them together. And then if r equals 0, this one goes away. Minus 2a0 times 0, that goes away. Plus 2a1 times 1. Minus 2a0 equals 0. So they're gone. And it looks like I get a1, 2a1 equals 2a0, and a1 equals a0. Nice. Okay, cool. I think I've done that right. All right. And now if I go to m equals 1, this has got an m equals 1 because it starts at minus 1. This has got an m equals 1 because it starts at 0. This has got an m equals 1 eventually because it starts at minus 1. This one's got an m equals 1. This one's got an m equals 1. Okay, so from m equals 1 upwards, they all have all of the terms. And so I'm just going to include them all from now on. So for m greater than or equal to 1, the coefficient of x to the m plus r. Now I just copy this thing down that I've got, but I'm going to sub in the r's as I go, and r equals 0. So let's see. All right. So when r equals 0, I've got an m plus 1 here and an m. This one's got a m. This one's 2a m plus 1, m plus 1. This one's an a m minus 1, and this one's a minus 2a m. And that's supposed to be equal to 0. So if I had to do it for both of the r's, I would do all of this in terms of r to start with, and then sub in afterwards. But since I was specifically asked to do it for r equals 0 and only for r equals 0, I'm good. Okay. All right. So now we make a recurrence relation. And the biggest m is m plus 1. So I'm going to rearrange to get a m plus 1 equals. Okay. Let's see. So there's an am plus 1 there and there, which my text is. So am plus 1 there and there, and an m plus 1. So I reckon I'll factorise that out. So I've got an am plus 1 times m plus 1, and I'm left behind an m and a 2. Okay, cool. And everything else I put on the other side. Okay. They've both got an AM there. So AM, 2 AM actually. M minus 2. Sweet. Unfortunately, it goes on to the next page, which is sad. Two m minus 2 am plus am minus 1 m plus 1 m minus. All right, that's what I've got. So this was for m greater than or equal to 1, which means I could do it this way if I wanted. So let's shift them all up by 1. No, down by 1. Crap. So minus 2 went down to minus 3, m went down to minus 1, m minus 1, m minus 1 went down to m minus 2, m plus 1 went down to m plus 2 went down to 1. Cool. And this would be m greater than or equal to 2. So these m's went down by 1, and this went up by 1, so that it comes out to the same thing. Okay, so there's my recurrence relation. Okay. Okay, so now I could attempt to figure out what the first several terms were. So my first terms, let's see. So A0 is A0. We didn't figure out what that was. A1 was equal to A0. A2, which is where this formula starts, was 2 times 2 minus 3, A1 plus A0 over 2 times 3, according to the formula. Sorry, I'm just checking back to see if my minuses are correct before I move forward. Okay. So okay, so A1 was equal to A0. So minus A0 on 6, apparently. Let me do the next one just to be sure. A3 is equal to 2 times 3 minus 3 times A2 plus A.
David?
Yes?
I think you've made a mistake in the AM plus 1 term.
Where?
No, on the other page.
Here?
Go up to the top. I think it should be to AM plus 1.
Here? Here.
No, up to M plus 1 rather than minus.
Oh, crap. Yes, you're completely correct. Minus 1. I was getting all worried because things were disappearing. So let's just go back and fix just a second. So I think we were correct at this stage. No, that's a plus, because this went over there. Minus Fairy's not doing her job. Thank you. So these are both minus, so when they went over there they became pluses, and that becomes a +1. Yes, it does indeed. And so when we do this, this is a +1, and this becomes an m. Yep. Because everything went down by 1. So down here this becomes a 2, and that becomes therefore a 4. Which is now 5A0 on 6. Okay, so my A3, 2 times 3A2 plus A1 over 2 times 3 times 4, which is 6 times A2, which was 5A0 on 6, plus A1, which was A0 over 12, which is whatever it is. Oh, that's not too bad, because 5A0 on 6 times 6 would just be 5A0. Huh. Not as bad as it seemed. Okay. Okay, so everything was in terms of A0, right? So for r equals 0, we get y is equal to, and we go all the way back to our beginning. And it was am x to the m plus r, but r is 0. So we've got a0 x to the 0 plus 0, which is just nothing, plus a0x plus a 5a0 on 6 x squared plus a0 on 2 x cubed plus and so on. Cool. And if the r had been a half, then there would have been an x to the half. There would have been an x to the half and an x to the 1.5 and an x to the 2.5 and an x to the 3.5, something like that. And if a had been -1, if the r had been -1, I would have gotten an x to the -1 and a constant, an x squared, and so on. Okay. Good-o. So, whoa, pitfalls, watch your minuses, my goodness. Don't try to do multiple algebra steps at once, 'cause it's not going to work. Yeah. So I'm just going to check that there's anything else on this. So, one thing that's worth looking at, if you look at past exams or practice exams, is that even though, so in Engineering Maths IIA, if any of you from Engineering Maths IIA are here or listening, they don't even talk about what to do if these differ by an integer or whatever. But in Differential Equations II, your lecturer does talk about that, but traditionally in the exams, they don't ever ask you to deal with it. They just ask you to do one of the R's and then the question stops. But just for completeness' sake, it wouldn't be the worst thing to just have a quick look at how that actually works. I'm just going to get my keyboard back. So, where's your lecturer's list of what to do? Don't tell me about the gamma function, I don't care. Indicial equation. Right, this is what the DE's 2 lecturer says about what to do. Two distinct roots not differing by an integer, just run with both of them. I did r equals 0 and I would do exactly the same thing for r equals whatever the other r is, and it would give me these two solutions. If you get a double root, then you will find the first solution with whichever, with your r, and then your second solution will be the original solution times ln x plus something else. But I don't know how to figure out what they are, what the other coefficients are. That's bizarre. Huh. And the third one, if they do differ by an integer, I don't even know how to find these other ones, and I don't think your lecturer actually showed you how to do it. Because presumably, see how this says capital A0, capital A1, capital A2, and this one says blah, blah, blah. I don't know how to figure out what this K and what these A naughts and stuff are. Do you think these are from the recurrence relation? Do you reckon? Maybe these are from the recurrence relation and there's, I don't know. I'm sorry, I don't know. And without an example to tell me what to do, I'm not sure I could figure it out, especially not on the fly in a revision seminar. If I had maybe a day or two to think about it, possibly. So I have a feeling that your lecturer will be happy for you to just write down the format, but I also have another feeling that it's much more likely that your lecturer will not actually ask you to do anything, and you'll just be asked to find what the first several terms are for the series for a particular value of r. Yeah. If you get r equals 0 as one of them, it's the most convenient one because it turns out that an ordinary series works after all. Yeah. But I thought I would at least mention it. Still don't quite understand what that means. I ran up to Barry after, it was Barry, wasn't it? If you're listening in future semesters, it might not be Barry anymore. I ran up to unless we change the name of the DE's lecturer to Barry every year. So I ran up to Barry after your revision seminar from him last week, which coincidentally was in the room I was coming into, and I asked him about it, and he said that he wouldn't ask you to find the other one. He might ask you to say what format it's in, but he won't ask you to find it. So, yeah. Good to know. Okay, that's Frobenius. Any thoughts or questions about that at all? Good. I should say at this point as well, these all have an A naught in them, which means you can sort of pull the A naught out the front, and you end up with this one linearly independent basis solution. And some of them, the recurrence relation doesn't actually tell you that everything's in terms of A naught, and you end up with things in terms of A naught and A1, and then you've already got your solutions and you can stop and you don't need the other initial equation. So that's cool too. All right. What time is it? Wow. All right. Well, I'll pop it on the EngMaths IIA site as well. Anything else from anywhere in the course?
I don't understand what you did when you use the earliest n to get the initial equation.
Okay.
I don't know if that's
So I was here, and I did the earliest m. Sorry? Wasn't it? I'm just going to look up in these lecture notes to see if that's what was done. But that's how I make the initial equation because it works.
I think the idea was that you put it into this standard set form, and then after doing one derivation, the initial equation always looks like a certain format, and then you can just sum it in.
Oh, okay. You can probably, there's probably a thing that gets it direct from the original formula. I'm just trying to figure out where the initial equation was mentioned in these notes, but there's probably more detail. This says we seek a solution of this form, which is what I did. Substitute, rearrange, and equate the powers of x. So that's the same as saying that all the coefficients are equal to 0. Since the coefficient a0 is not 0, the exponent r must satisfy the initial equation. Oh, okay. What are b0 and c0 in this case? They're just random things that turn up? Oh, that's this. Oh, okay. So they're saying that if it's x squared y double dash x bx and cx, if it's written that way, so if it's already got an x squared in this position, then you can just sub in x equals 0 into these things. But I didn't do that because I had to rearrange. This is my thing, right? It's just like when I do trig substitution. I have to do all this algebra on the trig substitution thing anyway, so I might as well use it to figure out what the trig substitution is. This is way back in Maths 1A. So I have to do all this rearranging with the linear ODE, like with all the sums anyway. And so the thing is that this one came about by putting getting one that had the A0 in it. And the A0 went with the earliest m. It went with m equals 0 in that case. But because I shifted everything over, my earliest m isn't 0 anymore. It might be -1.
Yeah.
And so for me, since I have to do all this work anyway in order to figure out what the recurrence relation is, I just find it easier to do all of this and then chuck in, find the earliest m that appears. And it apparently works. Have you got your notes?
I do, but there's nothing of it. Just, yeah. But, so you subbed in -1, but called it A0.
Well, when I subbed in -1, I ended up with A0 because it was m plus 1 on my screen there. M plus 1, when I put m equals -1, gives me A0. But I find it easier, rather than looking to find what does the m have to be to make A0, I just find the earliest m that's mentioned in the sum signs, and that will do the trick.
I think in this one you just ended up explaining it in the example, and it wasn't as clear as that.
So I guess what I'm saying is that the initial equation is not particularly special. When I'm doing the same thing I did last time and going, well, what if it was of this format? What would happen then? And I sub it all in and I rearrange stuff and I try my best to make it easy to figure out what the answer is. And I go, oh, well, since this all adds up to 0, then when I add up the appropriate coefficients, they have to add up to 0 as well. Because the whole function is 0. And so I'm not really looking at the earliest one. I'm just saying, well, you know, I'm just going to keep track of some of them. The different early m's might not appear in all of the things, and so they'll get slightly different equations. And so I just go, well, the earliest m has this one, and the next earliest m has this one, and after that, oh, they all have that one, so that'll just be working with it with an unknown m. And it turns out that the earliest one will tell you what r is. And that's just the way it turns out, because of we're treading the path that others have tread before us. Yeah. And so it's almost as if this is a bit sensational to give it a name of its own. Like the initial equation. It's like, it's just the first equation we came up with. Like it just happens to, it just so happens that it tells me what the r should be. Yeah. And it's probably only got a name because when people talk about their working, they go, oh, do you remember that because they have to figure it out when r is 0 and when r is -1, or whatever it is, when they get to the second one, they can say, well, now using the other root from the initial equation, it just allows them to refer back to the equation they had before. I think that's my idea. I'm going to stick with it. I feel good about that. But how does that make you feel? Yeah. Okay. Yeah. Cool. All right. So I don't know if this is how your lecturer sets it out, but I like lining things up. It makes it easier for me to do things. Cool. Okay. So the other question I had, so I had a couple of people talking to me about doing things like this. this sort of thing. And I hate to say it, but I'm sick of that. You must be as well, I'm sure. And there are many examples of that on the past revision seminars that you can get to from your website. I did want to do something I hadn't done before, which was making an attempt to figure out how to do systems of linear equations and to figure out what the system actually is. This will probably be horrible flailing. Power series. ...2014 exam I had here. So, just checking, you guys did systems of linear ODEs. And they turned into matrices and their eigenvalues and stuff. Okay, good. Just a second. Okay, so this is an exam question from 2014 apparently. I really don't know where to start, so I'm just going to hopefully get help from all of you. And hopefully, and look, that's how we feel in the exam. Right. So after we've allowed ourselves a couple of minutes of panic, we can start thinking clearly. I'm just going to read this. 2014 DEI's exam apparently. The serval is a member of the cat family that lives in Africa, pictured to the right. Hello, serval. Given on the next page is an extract from Wikipedia of a serval's reproduction and life history. Okay, so I'm just going to read all of it because sometimes in exams when they say that they're giving us a command to do something, they've actually done it for us. So, from the information in the extract on the next page, create a plausible age-structure differential equation, biological population model of the serval. Plausible age-structure differential equation, biological population model of the serval. Yeah, okay, I think I can make that grammatically correct in my head. Choose 3 age categories of kittens, juveniles, and sexually mature adults. Define T to be the time in years. Y1 is the number of female kittens less than 0.5 years old from when they begin to hunt for themselves. Y2 is the number of female juveniles between 0.5 years and 1.5 years, which is when they reach sexual maturity on average. And Y2 is the number of female breeding adults older than 1.5 years and dying at about the life expectancy of 10 years. Roughly estimate the coefficients in the model from the information in the extract and give reasons and do not solve the equations. Okay. Rightio. I'm just going to write some of that information down. Okay, T is time. Y1 of T is number of female kittens up to 0.5 years. Y2 of T is number of female juveniles from 0.5 years to 1.5 years. It's unfortunate that Y both stands for years and the number of female kittens. That's annoying. And Y3, number of female breeding adults, 1.5 years to 10 years. Okay. So if we're going to estimate this as a system of ODEs, then that should be something along the lines of the derivative is equal to crap involving the y1, the y2 and y3. So this is what's in my head. I'm thinking that our goal is to go y1 dashed, y2 dashed, y3 dashed equals stuff involving y1 and y2 and y3. That's what's in my head of what I'm trying to achieve here. Okay, that's good to know. Okay. I wish I had printed this out. But as I said, I didn't prepare very much. Of course not. Kittens are born. I will just use this 2/3 of my page. Kittens are born shortly before the peak breeding period of local rodent populations. Sure. A serval is able to give birth to multiple litters throughout the year, but commonly does so only if the earlier litters die shortly after birth. Okay, so we don't care about multiple litters then, because the other ones are dead. Okay, cool. Gestation lasts from 66 to 77 days, and commonly results in the birth of 2 kittens, although sometimes as few as 1 or as many as 4 have been recorded. Right, that seems like useful information about rate of change of number of kittens, the number that are born in a litter. So, number of kittens in a litter usually 2, but could be from 1 to 4. Okay. Not sure if this gestation period is going to be helpful. What was time measured in? Years. Okay, I'm just not sure about this one, 66 to 77 days. And the kittens are sort of all born at the same time of year by the look of it. It doesn't really, I don't know if that matters. So this first paragraph so far, we've got kittens in a litter, usually 2. There's that many days gestation. Kittens are born at roughly the same time of year. They're born shortly before the peak breeding period of local rodent populations. So they're all born at the same time of year. That's what I'm thinking. The kittens are born in dense vegetation or sheltered locations such as abandoned aardvark burrows. Yay. If such an ideal location is not available, a place beneath a shrub may be sufficient. That doesn't seem relevant to counting how many of them there are. The kittens weigh about 250 grams at birth. Who spells grams like that? And are initially blind and helpless with a coat of greyish woolly hair. All right, so I can recognise one if I see it. They open their eyes at 9 to 13 days of age and begin to take solid food after around a month. Around 6 months they acquire their permanent canine teeth and begin to hunt for themselves. Oh, that's the 0.5 years that they're talking about here, to 6 months, okay. They leave their mother about 12 months. They may reach sexual maturity from 12 to 25 months. Well, I don't understand. None of that information seems, I mean, that second paragraph seems to be what's creating these. All right, so I'm hoping that someone will be able to help me, because I've never done this before. But I wanted to see you notice that someone else struggles with this too. So, okay. Well, let's think about this. Y dashed 1 is the rate of number of kittens per year. That's what that is, because Y1 is the number of kittens, and the Y dash 1 is the rate of change of the number of kittens per year. So the breeding adults, assuming that all the breeding adults breed, then we should, and they all have 2 kittens, there should be 2 new kittens per existing breeding adult. Well, female adult anyway. So this is what I'm thinking that, sorry? Oh, yes. Oh, man. All right, we'll get there. Just a second. So we have each breeding adult produces maybe 2 kittens per year, and they would be, but one of them on average would be female, we're assuming, because half of the new kittens should be girls. That sounds reasonable. I don't think the fact that the gestation lasts from 66, oh bloody frail. I may have to adjust this. But I am thinking that therefore the rate of change of the number of kittens should be 1 times how many breeding adults there are. That's what I'm thinking. So if they had litters of size roughly 4, then there'd be 2 average female new kittens per adult, and so that would be 2 in this spot. Right, that seems reasonable. So Y2 dashed is the rate. Sorry? Oh, you're right. So the existing kittens would grow up. Yeah. So in the space of 1 year, all the existing kittens would grow up. Yeah, half a year. So what, 2 then? So, okay, just a second. So the change is 1 times Y3. Okay. But then every half a year, 0.5 years, the existing kittens become juveniles, and so the rate would be the number of kittens per half a year. Yeah? This is how many kittens grow up, but they do that every half a year. And so that would be 2y1. Okay. Wow, this is interesting. And so therefore I'm thinking that y1 dash should be y3 minus 2y1. New kittens being born at a rate of 1 per however many adults there are, minus that, because that's the rate of change per year of kittens into juveniles, because it's y1 per half a month. Yeah. Right. Okay, so y2 dashed is the rate of juveniles. So, juveniles don't get born, they just become juveniles from being kittens. And so this 2y1 that we had is the inward, you know, how many new juveniles are created. So, kittens 2y1 per year. Okay. But they're growing up into adults at a rate of 1 per year. Like, into adults. So there's y2 of them, and it takes them 1 year to do that, because juveniles are from half a year to 1.5 years. Okay, feeling good about this. And so y2 dash should be 2y1 minus y2. Right.
Wouldn't we be taking it in the space of the same year? So because we've got juveniles growing into, sorry, kittens growing into juveniles at a rate of, you know, twice per year, then you'd also refer to juveniles becoming adults at that same rate of, you know, every 1.5 years?
Fuck. I don't know. I have a plan. These are all good things, but I have no idea how to resolve the problem. You have the solution, but I have one other idea that might help me figure this out. In a moment. I want to do this before I see the solution, and then I'll try and understand the solution. Yeah. So just a second. So these are our servals. So, and here this guy's born, and then half a year later, and then they die, right? Okay. All right. I'm not going to draw becoming a breeding adult. So, so does that? The thing I was thinking was, I mean, the assumption I was having is that they're all born at roughly the same time, right? So, but the other thing I was thinking of, what if they're all being born sort of continuously at a certain rate? But that's not the truth. I'm going to look at the solution now. Because I was just thinking, if there are a heap of them, that they might, yeah, I don't know. I'm going to look at the solution. Sure. We've come to the end of trying to figure this out for ourselves, and it's now time to see the wisdom of people who have done it before. I still like my diagram, even if it doesn't help. Yep. B-E-T-L-E-R, only one T. And now the people watching can see a video of the sort of thing that happens live in the Maths Learning Centre, where David tries to figure things out that he's never seen before.
I think you're right, actually.
What's that?
Your solution was you pretty much almost there for your solution anyway.
Where's that solution from?
This is from the Maths Society, but they pretty much did exactly what you did, and then just finishing off with the last part.
Is it the same as the thing you're sending me? Okay. Anyone in Maths who's watching, though you probably aren't. I apologise, because, you know. Change the number of... Yeah, that's what I wrote. Change the number of juveniles. Change the number of adult... I mean, that's what I did.
Yeah, I said it was right.
Okay, good.
I think I was just getting confused between the, I guess I looked at it from a 0 to 1.5 as opposed to 0.5 to 1.5.
Yeah. It does seem a bit odd. Like that whole thing here is like... I mean, the thing is that we're doing something in continuous time that we've been told happens discretely, and so it doesn't make any sense to me. Yeah. Okay. But yeah, you're thinking, well, just a second, if it happens every half a year, then it should be... I've done this calculation, but really, I mean, if I'm looking over the space of a whole year, they've all matured by the end, so what's the deal? That's what you were thinking? Yeah. I don't know. I don't know. I would love to know what Barry thinks. Okay, that diagram's not really relevant. Okay, so in that case, change the number of adults per year. So new adults from juveniles, well, we just figured that out from before. That was the Y2 that we just did. And old adults die okay, so if it takes them 10 years to die, we're sort of going, one adult takes 10 years to die, so therefore we have 1/10 of an adult per year dying. That's what I would say.
Well, actually, I think it's, since we go from juveniles to adults, like,
Ah, right. So it's actually minus 1.5 years. So it's like 8.5 years. Okay. Old adults die. Okay, after 8.5 years of being a juvenile. So that's one adult per 8.5 years. So we have this on 8.5. And so therefore y3 dash should be y2 minus y3 on 8.5, whatever that is. It's apparently 0.12. Okay. And so y1 dashed is y3 minus 2y1, y2 dashed is 2y1 minus y2, y3 dashed is yeah. So if the thing that was confusing me is if the thing is that they're not all being born at exactly the same time. I mean, if they were always, there was like a rolling number of kittens being born at any given moment, then this would make perfect sense, right? So you go, well, it takes them half a year, and so the number that are currently here now, on average, we get one per every half. You know, it takes half a year for one, and so it would take, one for every half. Just a second, crap. Half a year is one serval maturing, and so that would be one maturing for every over half a year, like if flip it upside down. And that would make sense if they weren't all born at the same time, which is freaking me out. Sorry?
Maybe a lot of the kittens just die.
Maybe. Yeah. If they're all being born continuously, that would all make a lot of sense to me. And if that was true, I would probably try and work in the gestation period. because a single mother can only produce, they don't produce 1 litre a year, they produce 1 litre every 77 days, which would change that rate as well. So, I don't know. I think, however, hopefully it's not as complicated as this if you ever have to make one yourself, that this seems like a reasonable way of thinking about things. If the animals mature from one group into another at this time frame, then you have 1 per that time frame, and so that's the rate of change. So divide it as that to figure it out. Wow. Okay, I would feel confident to get at least half the marks in that question if I did the exam now, which is all I need. Yeah, and we are currently at, still 10 minutes to go. I could talk about something else. So the nice thing about this one is that not that the exam question explicitly said, do not solve this, but we could solve it because it's linear. So we could actually create a matrix from this point if we really wanted to. We can do that bit, and I can do this. So minus 2y1, no y2s, and y3, and 1y3. 2y1s, minus 1 y2s, and no of them. And no y1s and 1 y2s, and minus 1 on 8.5 of them. And now we have this wonderful matrix, and we can do the things. We could find solutions that would find some eigenvalues, do some e to the power ofs, and figure out some formulas for how much everything is. And if all my eigenvalues are less than 1, then they die. They all die out, depending on how many we're to start with, I suppose. All right, cool. I'll give this back to you before I forget. Any other thoughts or questions or things you want me to say? Because I can talk about PDEs if you really want me to. I still feel good about the fact that this helped me. As long as I knew what the y dash, I knew what I was looking for, so I needed to talk about the rate of change of each of them in turn. Yeah.